Welcome to sub-module 4 of 4 of risk management within our drilling optimization series. In this session, we'll explore how risk management principles directly shape drilling performance, costs, and outcomes. We'll connect engineering design with practical tools such as ranking, trees, and cost analysis, setting the stage for effective drilling optimization. In this module, our objectives are clear. First, we will distinguish between offset analysis and engineering risk analysis, understanding how each provides unique insights into drilling operations. Next, we will examine how risk has tangible economic impacts on drilling projects, influencing both cost and time performance. From there, we'll focus on the 4 key risk treatments: avoidance, control, acceptance, and transfer, each a critical part of the risk management toolkit. We will then introduce a set of practical tools such as ranking, decision trees, tornado charts, cost-time analysis, and the race E matrix, showing how they are applied to real drilling scenarios. Finally, we'll bring it all together by demonstrating how proper risk management leads to optimized drilling performance by reducing uncertainty, improving efficiency, and enhancing economic returns. This roadmap guides the rest of our discussion. When we talk about risk in drilling, it is important to separate offset analysis from engineering risk analysis. Offset analysis looks at what has happened on previous wells in the same field or region. It identifies trends such as stuck pipe events, circulation losses, or well control incidents, and then uses that information to forecast risks on the new well. Essentially, it is about learning from history. Engineering risk analysis, on the other hand, is forward-looking. It considers the technical design of the well, things like casing points, mud weight windows, and pressure regimes. This type of risk analysis evaluates whether the well design itself creates exposure and how those risks can be managed before the bit ever turns to the right. By combining both approaches, we get a balanced view of what could go wrong and how to prevent it. Next, we'll explore how risk analysis links directly into engineering design. Risk analysis must always be connected to the engineering design of the well. A design is not just a mechanical drawing. It's a set of assumptions about formation pressures, drilling fluid properties, casing strengths, and expected loads. If those assumptions are wrong, the design exposes us to risk. And the important question is, where does offset analysis fit? Offset analysis is a critical input to engineering design. For example, if offset wells in the same area show severe losses in the 12¼ inch section, that knowledge must inform the casing program and mud weight plan for the next well. Similarly, if offsets show higher than expected pore pressure, then the design must adapt to prevent kicks or well control issues. By tying risk analysis to engineering design, we make the plan realistic, grounded in both data and experience. We avoid designing wells that are theoretically perfect, but practically unsafe. The key point is that risk analysis is not separate from design, it is part of the design process itself. With this in mind, let's move into how risk analysis transforms into practical risk management. Risk analysis by itself is only the first step. What matters is how we use that analysis to manage risk. The slide shows the transition from analysis to management, where the economic and project impacts of risk become the central focus. Every drilling project has uncertainty, but not every uncertainty translates into risk worth managing. That depends on the potential consequences. For example, a minor delay of half a day may not matter in the overall economics of a long well, but the risk of stuck pipe, even if low probability, has a severe cost impact and therefore must be addressed. The tools we use to move from analysis to management include ranking, prioritizing which risks are worth our attention. Decision trees help us visualize different outcomes and choose the most economical option. Cost analysis quantifies what those risks could mean in dollars and days. Risk assessments provide a structured way of comparing threats, while tools like the race E matrix ensure ownership of decisions. On this slide, you'll see each of these tools listed, showing the progression from analysis to action. The key message is that risk management is about turning data into decisions. With this foundation, we're ready to look at the formal treatments of risk. Risk management always comes down to 4 basic treatments: avoidance, control, accept, and transfer. Each is simple in principle, but powerful in application. Avoidance means eliminating the risk entirely by not performing the activity. For example, if drilling a high-angle sidetrack exposes us to excessive torque and drag, we might decide to avoid that trajectory and select a more conservative well path. Control focuses on reducing the severity of a potential loss by putting safeguards in place, and this could mean using managed pressure drilling to control kicks or running a contingency liner string to reduce the chance of lost circulation escalating into a major well control event. Accept is when the team acknowledges that the risk exists and agrees to bear the consequences if it occurs. This usually applies to low-impact risks where mitigation costs more than the risk itself. Finally, transfer involves shifting the risk to another party through contracts or insurance. For instance, we may transfer risk to a service company by including performance guarantees. Next, we'll examine how human and organizational behavior influence risk decisions through risk aversion. Risk management is not only about technical tools, it's also about behavior. This slide introduces the concept of risk aversion, which describes how people and organizations act under uncertainty. A risk-averse decision maker will prefer a certain but lower return rather than take a gamble for a potentially higher but uncertain outcome. In drilling, that could mean choosing a proven, slightly more expensive mud system instead of a new, untested one that promises lower costs but carries unknown risks. Risk-neutral behavior is more balanced. Here, the decision maker evaluates options purely on expected economic value, without bias towards certainty or uncertainty. For example, if 2 casing programs have equal expected costs but different probabilities of overrun, the neutral manager treats them as essentially equivalent. Risk-seeking behavior is the opposite of risk aversion. A risk-seeking decision maker is more willing to take on uncertainty for the chance of a higher return. In drilling, that might be choosing an aggressive well trajectory in hopes of hitting more reservoir, even if it raises the chance of stuck pipe. Next, we'll look at specific tools that help us prioritize risks, beginning with ranking. Ranking is one of the simplest but most effective risk management tools. It allows us to compare different risks side by side and prioritize which ones deserve the most attention. For example, imagine a drilling project with risks such as stuck pipe, lost circulation, bit failure, and well control. If we rank them by probability and severity, stuck pipe may come out on top due to both high likelihood and high cost impact. Bit failure, while disruptive, may rank lower because it is easier and cheaper to address. The strength of ranking lies in its clarity. It provides a straightforward way to communicate risks to both technical and non-technical stakeholders. Instead of getting lost in numbers, we can say, these are our top 3 risks and this is where we will focus our mitigation efforts. The graph shows a cross-plot of wells compared to DD management and risk impact. We can then identify wells that are easiest to drill with the lowest risk. In this example, NSE-A0 and NSE-B0 are the 2 best candidates. By mastering basic ranking, we build a foundation for using more sophisticated tools like decision trees. That will be our focus on the next slide. Decision trees are a powerful way of visualizing choices under uncertainty. They allow us to lay out possible events, their probabilities, and the outcomes in terms of cost or time. This tool is familiar from other training sessions, such as the stuck pipe and fishing example. In that case, the decision tree helps us decide whether to continue fishing or to sidetrack. By assigning probabilities and costs to each option, we can compare which course of action gives the best expected outcome. Decision trees can be applied at many levels. At the single event level, they help us evaluate isolated problems, such as whether to pull out of hole when signs of pack-off appear. At the project level, they allow us to assess broader strategies, such as whether to invest in managed pressure drilling for an entire field campaign. The diagram shows a decision tree for a fishing scenario during drilling operations. The purpose of the tree is to help us decide whether to attempt fishing or to sidetrack immediately by comparing the economic consequences of each option. Starting on the left, we begin with the fishing scenario. This leads us to a decision node with two possible paths. The upper branch represents an attempt at fishing. That option leads to a probability node labeled EMV1, which stands for expected monetary value. From here, we have two possible outcomes, success or failure. If the fishing operation is successful, which happens with probability P1, the cost is P1 multiplied by A dollars. Here, a dollars represents the cost of retrieving the fish and resuming the well as planned. If the fishing attempt fails, with probability 1 minus P1, the cost becomes 1 minus P1 multiplied by C dollars. In this case, C is the higher cost of a failed fishing operation, which includes wasted rig time and usually the need to sidetrack anyway. The lower branch at the first decision node represents going directly to sidetrack. This has a fixed, certain cost of B dollars, with no probability attached. The decision boils down to comparing the expected monetary value of fishing, EMV1, with the guaranteed sidetrack cost, B dollars, which includes the lost in hole cost. Whichever option yields the lower expected cost is the rational choice. This tree shows how probability and cost can be combined into a structured decision-making framework for operational planning. With decision trees covered, we can now look at another tool for identifying uncertainties: tornado charts. Tornado charts provide a visual way to understand which uncertainties matter most to project value. They are based on sensitivity analysis, where we vary key input parameters such as drilling days, cost per day, or non-productive time, and see how much the outcome changes. The tornado chart here shows the sensitivity of reserves to different input parameters, with the base case at 4,291 marked by the central line. The key takeaway is that uncertainty in reserves is driven mainly by area and net pay because they drive the largest variation, guiding us to focus data collection efforts there. One of the most practical applications of risk analysis in drilling is cost-time analysis. Every drilling project is driven by two key variables, time and money, and risk analysis helps us predict their range rather than just a single estimate. The most common methodology is continuous probability. Instead of saying a well will take exactly 40 days, we acknowledge uncertainty by modelling a distribution. For example, we might say there's a 10% chance the well finishes in 35 days, a 50% chance it takes 40 days, and a 90% chance it could stretch to 50 days. This P10, P50, P90 framework provides a much clearer picture of reality. By applying cost-time analysis, project teams can better prepare contingencies, negotiate contracts, and align expectations with stakeholders. A contractor may prefer to plan around the P50 estimate, while the operator might budget closer to P90 to ensure funding covers worst-case scenarios. Continuous probability is not an abstract concept, it is a daily tool for forecasting. Next, we'll examine how risk assessment moves from initial identification to understanding residual risk after controls are applied. Risk assessment is the process of systematically defining, measuring, and deciding on risk. It starts with identifying hazards and assigning levels of probability and impact. This is what we call initial risk. Once prevention and mitigation measures are applied, such as stronger casing, better cementing, or improved monitoring, the risk level is reduced. What remains after controls are in place is called residual risk. The key question is whether this residual risk is acceptable. If residual risk is still unacceptably high, the operation or activity may not proceed. For example, if even after installing redundant barriers, the chance of a blowout remains above the organization's risk tolerance, the design must change or the project abandoned. The slide emphasizes this decision point. It reminds us that applying controls does not automatically make an operation acceptable. The residual risk must always be reviewed against organizational and regulatory standards. This framework is essential for transparent, defensible decision-making. From here, we'll turn to the RACE E matrix, which ensures responsibilities and accountabilities for risk decisions are clearly assigned. The RACE E matrix is a powerful tool for clarifying roles in decision-making and risk management. RACE stands for responsible, accountable, consulted, and informed. The responsible role belongs to those who actually perform the work or manage the risk directly. For example, drilling supervisors implementing a mudweight program. Accountable is the person ultimately answerable for the result, often the drilling superintendent or project manager. Consulted refers to subject matter experts or stakeholders whose advice is required before a decision is finalized, such as geomechanics specialists or safety engineers. Finally, informed includes those who must be kept aware of decisions but are not actively part of the process, such as operations, management, or partners. This matrix is vital in managing change. It avoids confusion about who owns each decision and ensures risk responsibilities are not overlooked. The key point here is that a well-structured RACE E facilitates understanding and enhances process efficiency. In drilling risk management, the RACE E matrix not only aids decision-making, but also facilitates the transfer of ownership where appropriate. Next, we'll expand this thinking into drilling optimization and discuss how risk management directly contributes to monetization and value creation. Ultimately, risk management is not an isolated activity. It directly contributes to drilling optimization and value creation. A key point is that risk control directly correlates to monetization. By systematically detecting, preventing, mitigating, and predicting incidents, we reduce both the probability and the impact of unwanted events. This leads to cleaner drilling times, fewer interruptions, and a smoother operational sequence. The end result is less money spent on non-productive time and lower exposure to costly accidents. Risk control translates directly into measurable KPIs, such as reduced flat time, improved rate of penetration, or fewer stuck pipe events. Beyond simply reducing incidents, risk management highlights optimization opportunities. For example, analyzing risk data might reveal that changing bit type reduces both vibration risk and drilling days, generating dual benefits. The key outcomes are cost reduction, process improvement, better ROI, and overall optimization of well delivery. The message is clear. Good risk management is not just about avoiding losses, it is also about capturing opportunities. As we move to the objectives review, let's reflect on how the tools we've discussed fit together to deliver safer, more economical, and more predictable drilling performance. At the beginning of this sub-module, we set out several objectives. Let's review how we've met them. First, we differentiated offset analysis from engineering risk analysis, showing how past well data complements forward-looking design considerations. Second, we examined the economic impacts of risk on drilling projects, emphasizing how uncertainty in time and cost affects overall economics. We then explored the 4 key treatments of risk: avoidance, control, acceptance, and transfer. Each was illustrated with practical examples relevant to drilling operations. From there, we applied tools such as ranking, decision trees, tornado charts, cost-time analysis, and the RACE E matrix, demonstrating how each supports decision-making under uncertainty. Finally, we connected these ideas to drilling optimization, showing how effective risk management reduces incidents, decreases cost, and improves return on investment. This review confirms that the sub-module has provided a comprehensive view of risk management, from theory to practice, within the context of drilling optimization. As we move to close, let's acknowledge that mastering risk is central to delivering safe, efficient, and profitable wells. That concludes sub-module 4 of 4 on risk management. Please proceed to the quiz to test your understanding of the concepts and tools we've covered. Thank you for your attention and participation. I look forward to building on these ideas as we continue exploring drilling optimization.